Welcome to the enigmatic and revolutionary world of quantum mechanics, the branch of physics that studies the universe's tiniest particles. This video essay will transport you through the history of quantum mechanics, from its early 20th century origins to its profound impact on modern science and technology. We'll explore the brilliant minds and groundbreaking experiments that have shaped our understanding of the quantum realm, a world that defies the rules of classical physics and challenges our perception of reality. In the closing years of the 19th century, the seeds of quantum mechanics were unwittingly sown by physicists wrestling with the behavior of light and matter. The journey began with Thomas Young's double-slit experiment in 1801, illustrating light's wave-like nature. Gustav Kirchhoff later established the concept of black-body radiation, setting the stage for a deeper understanding of light's interaction with matter. At the same time, Ludwig Boltzmann, James Clerk Maxwell, and others developed statistical mechanics, revealing the probabilistic underpinnings of thermodynamics. In 1887, Heinrich Hertz's discovery of the photoelectric effect challenged the wave theory of light, hinting at a more granular, quantum reality. This discovery laid the groundwork for one of the most pivotal years in physics, 1905, known as Einstein's Annus Mirabilis. During this year, Albert Einstein proposed that light consists of particles, now known as photons, and introduced his revolutionary theory of relativity. Meanwhile, Planck's work on black-body radiation in 1900 suggested that electromagnetic energy could be emitted only in quantized forms, an idea that clashed with the classical continuous theories of the day. As the 20th century dawned, these scattered pieces of a larger puzzle began to coalesce. Rutherford's gold foil experiment in 1907 revealed the nucleus, and the Geiger-Marston experiment of 1909 demonstrated the wave-particle duality of light. These discoveries, alongside others in the fields of radioactivity and atomic structure, set the stage for the quantum revolution that was about to unfold. As the 20th century progressed, the odd behavior of the microscopic world demanded a new kind of physics. In 1913, Niels Bohr proposed his model of the atom, introducing quantized orbits for electrons, which could only exist at certain discrete energy levels. This model successfully explained the observed spectral lines of hydrogen, a profound step towards quantum theory. Meanwhile, experiments like those of James Franck and Gustav Hertz in 1914 provided crucial evidence for these quantized energy levels by bombarding mercury atoms with electrons and observing discrete energy emissions. In the same period, the theoretical groundwork for quantum mechanics was being laid down. Arnold Sommerfeld extended Bohr's model, introducing elliptical orbits and fine structure corrections, while others like Louis de Broglie began to blur the lines between particles and waves, suggesting that electrons could exhibit wave-like properties. This wave-particle duality was a radical departure from classical physics, yet it was essential to understanding the quantum realm. The year 1925 marked a turning point with Werner Heisenberg's introduction of matrix mechanics, the first complete and consistent theory of quantum mechanics. This was rapidly followed by Erwin Schrödinger's wave mechanics, which described the behavior of quantum particles as waves. The equivalence of these two theories, seemingly different in formulation but identical in physical content, was demonstrated through the work of Schrödinger and others, uniting the particle and wave descriptions into a single quantum framework. These early quantum theories were confronted with a strange implication, the uncertainty principle, articulated by Heisenberg in 1927, which posits that certain pairs of physical properties, like position and momentum, cannot be simultaneously known to arbitrary precision. This principle challenged the deterministic nature of classical physics and introduced a probabilistic element to the fundamental laws governing the universe. The philosophical and scientific implications of this principle are still being explored and debated today. The interwar period was a golden era for quantum mechanics, as the theoretical framework became more rigorous and began to explain a vast array of physical phenomena. In 1927, the Solvay Conference brought together the most brilliant minds in physics, where heated debates took place, notably between Einstein and Bohr over the stochastic nature of quantum mechanics. The conference marked a turning point, solidifying quantum theory as a dominant paradigm in physics. During this time, the principles of quantum mechanics were refined and expanded. Paul Dirac formulated the Dirac equation in 1928, reconciling quantum mechanics with special relativity and predicting the existence of antimatter. This was not just a theoretical curiosity. In 1932, Carl Anderson experimentally confirmed the existence of the positron, an antiparticle of the electron, a landmark discovery confirming Dirac's predictions. The development of quantum mechanics also prompted questions about the measurement problem and the role of the observer in the quantum world. The Copenhagen interpretation, largely developed by Bohr and Heisenberg, presented the idea that quantum particles do not have definite properties until they are measured. This interpretation became one of the most discussed and debated aspects of quantum mechanics, laying the philosophical foundations of the theory. In 1935, Einstein, Podolsky, and Rosen published their famous EPR paradox paper, challenging the completeness of quantum mechanics and arguing for hidden variables that could restore determinism and locality to the theory. In response, John Bell developed Bell's theorem in 1964, which proposed a way to test the presence of these hidden variables, leading to experiments that supported the quantum mechanics framework and demonstrated the non-local nature of quantum entanglement. The maturation of quantum mechanics was not just of scientific importance, but also had profound implications for technology. The understanding of quantum phenomena underpins much of modern electronics and materials science, leading to the development of semiconductors, transistors, and lasers. The quantum leap made during this period was not just a step, but a giant stride into the modern age. In the aftermath of World War II, quantum mechanics continued to evolve, intertwining with the fabric of modern society. The invention of the transistor in 1947 by Bardeen, Brattain, and Shockley revolutionized electronics, paving the way for the digital age. This seminal innovation was rooted in quantum understanding, manipulating electron flow at the smallest scales. The subsequent development of the laser in 1958 harnessed the principles of quantum electronics, altering communication, medicine, and industry. The latter half of the 20th century witnessed the rise of quantum field theory, which reconciled quantum mechanics with the theory of relativity and paved the way for the standard model of particle physics. The discovery of quarks and gluons, the fundamental particles that make up protons and neutrons, confirmed the predictions of quantum chromodynamics. As the century progressed, quantum mechanics continued to be the cornerstone of new technologies, including semiconductor chips and quantum computers, which promise unprecedented computational power by directly leveraging quantum states. Today, quantum mechanics is not just a theory. It's a toolkit that engineers and scientists use to design new materials and devices, from solar cells to MRI machines. It's a testament to the quantum leap made by the pioneers of physics, whose curiosity about the nature of light and matter has shaped the modern world. As we peer into the 21st century, quantum mechanics continues to challenge and inspire. The quest for a grand unified theory that can seamlessly integrate gravity with the quantum world leads researchers into the enigmatic realms of string theory and loop quantum gravity. Quantum entanglement, once a peculiar implication of quantum mechanics, now underpins emerging technologies like quantum encryption and teleportation, potentially revolutionizing secure communication. The nascent field of quantum biology probes into life cellular machinery, suggesting that quantum effects might play a role in phenomena like photosynthesis and avian navigation. Meanwhile, quantum cosmology attempts to decode the universe's deepest secrets, looking at the Big Bang and black holes through a quantum lens. As quantum technology advances, we stand on the brink of a new technological era, one where quantum sensors could redefine precision measurements, and where quantum simulations might unlock mysteries from superconductivity to the human brain. The journey of quantum mechanics, from a curious set of ideas about the behavior of light to a cornerstone of modern physics, reminds us that our quest for understanding is far from over. It's a vibrant, evolving story, one that invites each new generation to question, explore, and imagine. As we close this journey through the history of quantum mechanics, we stand in awe of its mysteries and potentials. Quantum mechanics has not only reshaped our fundamental understanding of the universe, but also continues to drive innovation in countless fields. From the smallest particles to the grandest cosmic phenomena, it remains the most accurate description of the natural world we have. The quantum story is far from over. And the future is as uncertain and exciting as the particles that quantum mechanics seeks to understand.